Now we'll be dealing with a couple of polymers and we'll be discussing them one by one. So here we'll be dealing with addition polymers. You've already discussed them before, the addition polymers, and we know that addition polymers were the ones where no smaller units were being eliminated. So we'll be dealing with some examples. Now the first example we'll see of polythene. So the monomer was ethene, that is CH2 with a double bond and CH2 again. And this ethene, when certain conditions are being fulfilled, transforms into the polymer, and the polymer is polythene. So polythene polymer is something like this. So the double bond opens and we have got connections at both the side. N units of monomer we take, we get N units in a straight chain, that is the polymer. So the monomer is ethene and we obtain polythene. So now this polythene we discussed can be of two types, the low density polythene and the high density polythene. Here, if we are making the low density polythene, there are some conditions which we have to fulfill. That is, the temperature should be 350 to 530 Kelvin. That is high temperature we are providing alongside high pressure. So 1000 to 2000 atm, that is atmospheric pressure we are providing. Also, the catalyst, we have traces of O2. So traces of oxygen are inside. So now the polythene which is being developed is low density polythene is the polymer, and this low density polythene we refer to it before as LDPE, low density polythene. So if the conditions are 350 to 530 Kelvin and a high pressure, as you can see, we get LDPE. Now this LDPE is a low grade polymer. As the name suggests, it is low density polythene. So the chains, that is the polymeric chains, will be having low density and they will be not in very much contact with each other. Now contrary to this, we have the second type of polythene which we discussed, which was the higher density polythene. So here also the monomer is the same. The only difference comes in the condition that we are subjecting it to. Okay. So here also the polymer which is being formed is polythene. So it is CH2, single bond CH2 and N units yielding N units. So here also what happens is that we get polythene. Now the conditions here are certainly not similar to the previous case, as here the temperature is from 330 to 350 Kelvin. So low as compared to the previous case. Also the temperature drops to 1 to 2 atmosphere. So a huge difference that we are seeing from the previous case. So 1 to 2 atmosphere, it is the pressure here, and special catalyst we use here. So the special catalyst that we use over here is known as Ziegler-Natta. We'll be dealing it with a little later. So called Ziegler-Natta. Now here what we are getting is the polymer which we are obtaining is called high density polythene. This high density polythene is referred to as HDPE, that is high density polythene again. And as you can see, the temperature here is very low when compared to the previous case. And because this temperature is low, so this process of conversion of ethene to polythene, that is high density one, will be completed in a very long period of time, and hence the cost of production will automatically rise. Also, because the process is taking place at a low temperature and the cost of production is rising, the process itself is very, very slow. Because of this slow process, what happens is no branching is seen when development of this high density polythene occurs. And because there is no branching, therefore this is of high quality when we are comparing it to the previous case of low grade polymer, that was LDPE. Now, if we see here in this HDPE, what happens is, since it is of high density, what happens that the polymeric chains here will be in contact with each other, that is, they will have a high density, and since they are very compact, this HDPE is tough. So this is HDPE, that is high density polythene, and because of this compactness it makes it tough. Now, so a lot of examples which you can see of this HDPE are buckets. For instance, buckets are made of plastic, and that plastic is high density polythene. Now, contrary to this, the polythene that we previously saw was low density polythene, LDPE. Now, in LDPE, what happens is that polymeric chain, when formed because of the joining of many monomers of ethene, looks something like this. So we have n units of this. Now, when this happens, because this was not developed at a low temperature, and the process being fast itself in itself, because of the high temperature and high pressure, branching occurs. And what type of branching? So if we see it going through radical mechanism, so imagine a radical being developed over here, and the next, that is the connection, rises from here, and imagine another polymeric chain being developed from here. So as you can see, branching is happening at this certain LDPE, that is low density polythene, and because of this branching, the structure will look something like this. So there will be branching in this structure. Now, because this is a branched polymer, we know branched polymer will not allow the polymeric chains to come in contact with each other, and therefore low density is a feature of this kind of polymer. So low density, that therefore the name LDPE. Also, because of this low density, it is of low quality. So the quality is also degrading. Now, because the quality is degrading, therefore it is a low grade polymer, and this is used to make polythenes that we usually carry for as carry bags. You can see this type of polythene being used. The packing bags are made up of this LDPE. Because of this low density, it is cheap also, as you can see, because it is produced in large quantities, and we don't need a very high cost of production for this, because the process itself is fast, and this quality, this kind of polythenes are used for processes like packing bags and carry bags, etc. Okay, now coming on to the next example of addition polymerization that we'll be seeing. So here we are taking a monomer CH2 double bond CH, and then we have CH3. So here in this, the monomer that we have taken is known as propylene. Okay, so n units of this propylene we are taking, and what happens is that on polymerization we get the polymer which is of this sort. So we get the polymer, that is CH2 along with a CH open at the other end, and we have CH3 attached over here. N units of this we get. Okay. Now this polymer is called polypropylene, because poly means many and propylene comes from the monomer name. Now this polypropylene over here, what happens is that a catalyst is being used to carry out this reaction, and this catalyst is the Ziegler-Natta catalyst. So the Ziegler-Natta catalyst is being used. Okay, and this is a type of polymer, again addition polymer. So because it being an addition polymer, what happens is that it will, if we see it going through radical mechanism, imagine a radical being developed over here for attachment. Now because of this radical, there will be many chiral carbons occurring, and these chiral carbons will be randomly oriented so the quality degrades. That is why we are using the Ziegler-Natta catalyst to upgrade the quality of this product that we are getting, the polymer. So why are we using this Ziegler-Natta catalyst? Because the development of radicals will lead to many chiral carbons, and these chiral carbons will be randomly oriented, so the quality degrades. Okay, so you just write a short note about Ziegler-Natta over here. That is Ziegler-Natta. Now, what is the Ziegler-Natta catalyst? It is nothing but ET refers to ethyl group. So, and then we have TiCl4. So, this is the representation of Ziegler-Natta. Now, because of this Ziegler-Natta catalyst, what happens is this Ziegler-Natta catalyst prepares high quality material. So, it prepares high quality material with proper orientation. So the randomly oriented chiral carbon that we were actually getting, the orientation is made proper with the help of this Ziegler-Natta catalyst. Okay, so for proper orientation and high quality, we are using the Ziegler-Natta catalyst. So because of the Ziegler-Natta catalyst, let us just remove the chiral carbon that we developed. And now this is the third example of addition polymers that we are seeing.